I am László Csernai, nuclear physicist and external advisor in the Nanoplasmonic Laser-Induced Fusion Energy project. In short, it is NAP-LIFE. And I say a few sentences about why do we use nanoplasmonic antennas or nanoantennas for our fusion experiment. The present laser fusion experiments, probably without any exception, are using relatively slow mechanical compression to achieve high pressure and high compression with igniting one usually central point of the fusion fuel, which then spreads and sometimes even develops instabilities due to the slow process, and only a little part of the fuel target is ignited because the expansion due to the high pressure is moving faster out than the burning of the fusion. And we try to make a very different approach, not mechanical but radiation-dominated expansion. The other physical comment what one should mention, which is more or less should be known to physicists, is that there are two forms of energy. Mechanical energy, this is the same as electric or water or gravitational energy, as well as heat, or the other is heat. The difference is that mechanical energy can be transferred to heat with 100% efficiency, but heat can be transferred to mechanical energy only with big losses, that is about 2/3 in present situations. 2/3 of the energy is lost when we thermalize incoming thermal energy. So that is what we want to avoid. The basic obstacles of the present fusion project is that they are making a mechanical compression system with the laser light. The fusion fuel is even surrounded by a hard reflecting diamond type of surface to make the pressure and the compression is larger. And this allows sufficient time for compression, and we reach a compression which is 800 times of the original fuel, which is usually a low temperature deuterium tritium fuel. And then you get an ignition in the central point, and then this is then spreading, but only a smaller portion of the target fuel. Still, at the Lawrence Livermore laboratory, one could already reach up to about 5 or 6 megajoule fusion energy produced. Of course, the energy which is used for the whole experiment is still much larger. We try to avoid these obstacles in our project, and our solution is completely different and unique. We try to make a radiation-dominated ignition. Namely, we do not compress the fuel, or just minimally, and instead we irradiate the target. To avoid large compression, we have to have a transparent target, and we try to achieve equal and uniform ignition energy density in the target. And to achieve that, we have to use some tricks which are known in nanotechnology. That is implanting small nanoantennas into the target fuel. Antennas are well known to receive and absorb energy from the electromagnetic radiation, like the laser energy, which is monochromatic, just like the TV broadcast. And the TV broadcasts in the usual so-called Yagi antennas are collecting this energy, and that is which then transferred into a TV picture which everyone could see. Now, in the case of lasers, the electromagnetic radiation is the same and monochromatic and has one polarization, but the laser wavelength is much shorter. It's about 9 orders of magnitude, so 9 and then a 1. So that is a much smaller frequency. Therefore, the antenna is also should be much smaller. It is in the order of 80 nanometers, and it is also somewhat bigger diameter than the normal antennas. So the the bandwidth of the antenna is also larger. With this way, we put sufficient amount of the antennas in a way that if we have a very short igniting pulse, then both the side and the middle of the antenna should receive the same amount of energy, so we can achieve simultaneous ignition and much faster ignition than the present experiments. We, in this way, actually directly can accelerate by these nanoantennas protons and could achieve, without thermalization, relatively monochromatic and monodirection acceleration of the protons along the direction of the nanoantennas. With this kind of nanoantennas, we could achieve nuclear reactions already in the target. That means that, for example, we made deuterium, and even the target we could achieve and even measure the existence of in the targets we could achieve produced deuterium. And recently we also achieved fusion with targets where in the target material, a part of hydrogen, we had sufficient amount of boron, and then a special type of nuclear fusion experiment was achieved and nicely proven in recent experiments at the Szeged European laser infrastructure with the attosecond laser pulse. It's important and unique that we needed these very short pulses, because this is close to the time period of one wave of the laser radiation, and this is why our project is unique, because usually the lasers which are used for fusion are in the range of nanosecond, while the range of the pulse width in Szeged, it is attosecond, or that means that even less than 1 femtosecond. And therefore our project is highly unique. No other project is using this kind of resonant nanotechnology so far, and we hope that with increasing the target size and the amount of energy, we will show that this is a perspective and the best way of energy production, and we are not losing at most steps of the fusion and energy production process energy by thermalization. So that's what I wanted to describe. Thank you for the attention.